Okay. We will continue with our examples. Okay. We will consider the following example. The integral over C. C will be a closed curve, y over x squared plus y squared, dx minus x over x squared plus y squared dy. So this is the integral we want to evaluate. Well, we will have two cases. Firstly, C is the circle with radius 1 and center at 2, 0. Well, if I say nothing about the direction of the curve, remember by default we were taking the counterclockwise direction, but here I will specify it, oriented counterclockwise. Okay. Now in this case, let us look at the picture roughly. Okay, x is 2, and y is 0, and the radius is 1, so it's something like this. And it's counterclockwise oriented. This is our C now. Okay. Now, of course, the first thing we should consider always was see if we can use Green's theorem, because that would simplify the calculations. Here, of course, q sub x will be, forgetting the minus, okay, 1 x squared plus y squared minus x 2x divided by x squared plus y squared squared, and p sub y, okay, would be 1 x squared plus y squared minus y 2y divided by x squared plus y squared squared. And we see that here we have y squared minus x squared, and here we have x squared minus y squared over the square, but we had a minus sign here, so this is actually negative of this, so it is x squared minus y squared, and therefore they are equal. Well, they are not equal everywhere. We should be careful. Namely, okay, of course they are equal at all points except at 0, 0. Because at 0, 0, they don't exist. Okay, if they don't exist, they cannot be equal, of course. So we have a problem there. However, okay, this C, okay, does not contain the point 0, 0 inside it. In other words, okay, if I choose some open domain like this, say some D. Now, inside this D, P and Q have continuous partials everywhere, and they are equal. Okay. And, okay, this curve itself is in D, but also its interior is in D. So this says, at least as far as C is concerned, we can apply Green's theorem. So here, since on C and inside C, okay, that's inside the region bounded by C, okay, PQ have continuous partials, and Q sub x is P sub y. So Green's theorem being applicable, we get, okay, the integral is the double integral over R of Q sub x minus P sub y dA, but this is 0, so this is 0. Okay, so we are finished. Okay, the point, well, we could apply Green's theorem. Now, as the B part, this time, let C be the unit circle, counterclockwise oriented, okay? So it's a nice smooth curve, it's simple, well, it satisfies properties of Green's theorem. But PQ do not. Namely, okay, P and Q, okay, do not have, okay, continuous partials in the region bounded by C, namely because of this point. That point is in the region bounded by C, and PQ do not have continuous partials there. Well, this means that, so Green's theorem cannot be applied. Okay. Functions are the same, but the contour, the curve, okay, is changed, and now we have a problem inside the region. Okay, we cannot use Green's theorem. What else can we do? Well, one thing which always works is parameterize and calculate. So, okay, we parameterize C. Well, a standard way, as we are familiar by now, is cosine to sine t, and t runs from 0 to 2 pi. Note that direction is correct. As t increases, is counterclockwise. So it's okay. So everything is fine. We can directly calculate the integral. So let us proceed that way. And so our integral will be 0 to 2 pi. That's the interval of t. Okay. And we have, well, y, that is sine t, divided by cosine square t plus sine square t, and dx, which would be minus sine t, okay, plus, actually, minus cosine t divided by cosine square t plus sine square t, and dy, which would be cosine t again, and we have dt. Well, first of all, at the bottom, in the denominator, we have 1's, and at the top, we have minus sine square minus cosine square, so this is actually minus 2 pi. So it's not 0, as in the previous case. So this depended on, okay, the region containing inside, that's the curve, containing inside it bad points. Now, in such cases, we cannot use Green's theorem, but we can sometimes bypass still use Green's theorem to our advantage. Okay, this will be, say, 6th problem. Now, the question is, you can take it to be the same, but I will change one thing. The question is to calculate this. And C is, okay, counterclockwise oriented. Okay. Unit circle, okay, oriented circle, centered at 0, 0, with radius, okay, say 2. Okay. Now, first of all, as in the previous case, we can calculate these things. I will not perform the calculations, but you can check them for yourselves. That is, Q sub x is P sub y, except at 0, 0 by direct calculation. We can verify this very easily. Well, so we have this equality, but we have the bad point 0, 0 inside our circle, that is C. So this means that, okay, is in the region bounded by C. So Green's theorem cannot be applied. Okay, so what can we do? Well, we can parameterize. Okay, as before, namely polar parameterization, but the radius is 2, so we have 2 cosine t, 2 sine t, and t is from 0 to 2. Now, if we evaluate our integral now using this parameterization, we come across the following, okay? Well, we had y, so 2 sine t, divided by 4 times x is 2 cosine t. So this would be 4 cosine square t plus 4 sine square t, okay, minus x would be 2 cosine t divided by the same thing, namely 16 cosine square t plus 4 sine square t. Okay. Now, you immediately observe one difficulty. Okay. The difficulty is, okay, as in the previous case, okay, or unlike the previous case, and in the denominator, we don't have a constant. Okay, in the previous one, we had 1. But here, we have a very, you can take 4 out, but you have 4 cosine square plus sine square, which of course is not 1. It's 1 plus 3 cosine square t. Okay. Now, this, of course, has some difficulties, well, but using integration techniques, we can still manage this. Okay, let me just remark that this can be calculated actually, I did not do it very correctly, I suppose. yes, I missed dx and dy. Yes, dx would be minus 2 sine t here, and dy would be another 2 cosine t. Right. But still, this can be calculated using, okay, techniques of integration. Okay. But it's quite a long thing. Actually, you have sine squared t at the top. You have, or rather, yes, you can combine them. You have a constant at the top, but at the bottom, you have 1 plus cosine squared t, 3 cosine squared t. Now, if you remember, this can be calculated using the tangent x over 2 substitution. So, using such techniques, you can calculate that, but it's a long process. So what's going wrong? Now, what is going wrong is that instead of an ellipse as our C, we have a circle. That's the trouble. If instead of a circle, we had the ellipse, okay, 4x squared plus y squared is equal to something, then at the bottom, we would have constants. So life would be easy. Okay. So life would be easy. Okay. Similar to previous calculation. If C were, okay, 4x squared plus y squared equal to a constant, say 1 or whatever. Why? Because if C were this, then the bottom would be 1 or a constant, and integration would be very easy. Okay. Well, can we change these curves? Well, this is a quite standard trick in line integrals. Okay. Consider the following. We have a circle of radius 2, and say we have the ellipse. Now, this is our C. Now, I will put the ellipse there. Well, in the ellipse, x can be 1/2 at most, and y can be 1 somewhere here. So the ellipse is something like this. Okay. I will call this curve C1. Now, let me draw some auxiliary curves and go as follows. Okay, suppose I start from this point. Okay, I move, say, up to this point again. It's the same point, of course, but to make it more representable, I use it this way. And then I will go down here. Okay. Now, I will trace the ellipse in this fashion, come to this point, and then go up. Okay. So what do I have? Well, I have added, actually, the outer one is C. The inner one is C1. They are already given, or negative of C1. These are the new ones, so call them C3. If this is C3, the other one is minus C3. Now, even though C3 and minus C3, okay, are the same curves, okay, you can regard them as different curves separated. But by coincidence, okay, the two edges are on top of each other. So break from here and just separate that in your mind. Now this tells me that I have a C total, which is, okay, this curve, which is actually C, plus I have C3, plus I have this curve, which is the opposite of C1, and then I continue with minus C3. Now, this is a piecewisely smooth, certainly, closed. Okay. And, well, simple, well, it is simple in the following sense. I regard C3 and minus C3 as different curves. Okay? Yeah. You can think of this as, okay, opening a canal. Okay. And with this canal, okay, this point 0, 0 is thrown out. Okay. Now, what else do I have? Well, remember in Green's theorem, okay, C must be oriented counterclockwise. That means the region enclosed by C is on the left of C. Well, the region enclosed by C on the left of C is precisely this one. This is my R. Okay. It is bounded by CT, it's on the left of CT, and 0, 0 is not enough. Okay. And CT encloses R, okay, which is a nice curve, a nice region in which, okay, Q sub x is P sub y. Okay. That means now CT is a closed curve. Inside it, these have continuous partials, and they're equal because 0, 0 is not inside CT. Okay. Which means that I can use Green's theorem. Which says that the integral over CT is integral over R of Qx minus Py. But in R, this is 0, so this is 0. Now, this does not give me my result yet, but it tells me the following. Now, 0 is the integral value on CT, but let us look at CT. It was integral C plus, okay, integral C3 minus, that is on C1, integral C1 minus integral C3. And now I know this is 0. But I know something else. Integral over C3 is canceling with negative of it. And what this says is that integral over C1 is the same as integral over C. Now, this is an important result, and this has nothing to do with our particular example. Okay. Namely, okay, if you have a problem point, okay, just one single point, as in this example, at 0, 0, the closed curve you draw around it does not matter. All line integrals these are closed, of course, are equal. Okay. So this is a property about the bad point, and that you go once around it. It doesn't matter how you go around it, on which curve, okay, as this argument shows. And so, using this trick, we can assume that C is taken as C1, doesn't matter, and so we integrate over the ellipse. So instead of integral C, we can evaluate integral over C1. Okay. Now, C1 is the ellipse. Okay. It's the ellipse. So I can take as formulation of it, okay, 1/2 cosine t, sine t, t in 0, 2 pi. Orientation will be correct, just like a circle. I only put a constant. Of course, now, in this ellipse, okay, 4x squared plus y squared, okay, well, x squared is 1 over 4 cosine squared, so it's equal to 1. Okay. Well, this is what we wanted. So, okay, we get 0 to 2 pi. Okay. Now, going back to the example, we had y over, well, y is 1/2, y is sine t, and dx is minus 1/2 sine t, divided by, okay, 1 now, minus, where x over, well, x is 1/2 cosine t, dy would be another cosine t, and I have 1 here, and so I have dt. So all this says is that I have minus sine square minus cosine square, which is minus 1. So it is 1/2 times minus 2 pi. It happens to be minus pi. And this is the same as, C, okay? This is integral over C1. So, okay, if the curve is not good for calculation, if we have a bad point inside, well, we can change it so that it becomes a good curve. Okay? This argument is D1. Now, by the same token, we can further generalize it. Actually, if you have, that means if you have more than one bad points, you can argue exactly in a similar way. Such regions are called multiply connected. Well, the name is not important at this point. This argument, if we have, okay, more than one bad points. Okay. Well, but still, Q sub x is P sub y, okay? This is important. I mean, this is not exactness in general, but almost exactness, except at one point, okay? Except at the bad points. Namely the following. Okay. Suppose we have two bad points, P1 and P2. And we have, okay, a curve containing both bad points. Okay. Now, what can we do here? Well, firstly, okay, we can dig two canals. In other words, okay, say we start from this point, okay, we cover our C, okay, and then we have a canal here. Call this, say, C1, or rather, yes, C1. And then we go around this point, okay. Let's see, how should we go? Well, yes. Well, I have to change it anyway. So, okay, let me go this way. And then, okay, from this point on, I can move to the other one and make a round curve around it and go this way and come back. So by opening up a long canal, I put both points outside. Okay, give names to these. Say this is C1, this is minus C1. And then I have this part, and then this part later. So there's sum total will be some, say, C1 prime. And say this one is C2 prime. Okay. Let me continue this way. This would be some C2. This would be minus C2. And then I will go around this, come back, and continue this way. So, CT, I'm just repeating the same argument with two bad points. So, CT would be the following. First of all, I started from here and came back to the same point. I have C. And then I applied C1. And then, okay, I applied this, but later I will apply this part. So together they will make C1 prime. And then I have C2. And then I have minus C2 prime in the opposite direction. And then I have minus C2. And then together with the previous piece, I have C1 prime. Actually, yes, I want this to be counterclockwise. So I have negative of C1 prime. And finally, I have negative C1. Now, when you integrate, this, of course, says the following. Integral CT would be integral C plus integral C1 plus integral C2 minus integral C2 prime minus integral C2 minus integral C1 prime minus integral C1. Of course, C1s and C2s will cancel out, okay? And this was 0, okay? Again, by Green's theorem. Okay, because I can use Green's theorem, okay, to the region bounded by CT as a whole, which means that I'm considering this part except these circles. So this would say that, okay, this would say that integral over C would be the sum of these two. So what is the generalization? If we had one point, it would mean that the curve C1 prime is not important. You can take C or C1 prime. But if you have 2 points, well, you have to add them. If you generalize this further, of course, if you had 5 bad points and you drew curves, closed curves around them, 5 of them, then integral of C would be, over C, would be the sum of the 5 integrals. So this can be generalized to more than 1 point. Now, let us see this on an example. Okay. I will call that C prime. Okay. The example is the following. We want to calculate this integral of y over x squared plus y squared plus twice x minus 2 over x minus 2 squared plus y squared dx plus minus x over x squared plus y squared plus 2y over x minus 2 squared plus y squared dy. Okay. Now we observe, by direct calculation again, these two, okay, have the property q sub x is p sub y, and the derivative of this with respect to x is the same as the derivative of this with respect to y. In short, okay, if this is p and if this is q, then okay, q sub x is p sub y, except at the point 0, 0 and okay, 2, 0. So we have 2 problem points because we combined the 2 integrals. Okay. Now, suppose okay, we want to find the integral over C1 of this above p dx plus q dy, okay, where C1 is this one. Well, it has a value, of course. What is that value? Well, you can calculate that because of the following. Firstly, the second terms added together gives you 0. Why is that? Well, because it's exact. And the bad point, 2, 0, is well outside of this curve. It's not inside it. So, okay, I can take a region like this. In this region, the second parts are exact, and Green's theorem is applicable to that part. So that will give you 0. Okay. But for the first part, okay, we can calculate this. So I will repeat it as follows. Okay. Well, this integral is the same as the integral over C1 of y over x squared plus y squared dx plus minus x over x squared plus y squared dy, because okay, the integral over C1 of the second part, 2x minus 2 over x minus 2 squared plus y squared dx plus 2y over x minus 2 squared plus y squared dy is 0 by Green's theorem, which is applicable here. Since 2, 0 is not inside C1. Okay. So we can calculate that. Okay. So it is A, say, by direct calculation. Now, as B, okay, let us calculate C2 P dx plus Q dy, where now C is, okay, this curve. C2 is this curve. Now, in this case, of course, P dx plus Q dy is the same as integral over C2 of the second part. Okay. Because we have a problem there, all right, but let me write them separately then. Y over x squared plus y squared, okay, dx, okay, minus x dy over x squared plus y squared, plus, okay, the second terms, that is 2x minus 2 over x minus 2 squared plus y squared dx, plus 2y over x minus 2 squared plus y squared dy. I separated the integral into two. Now, this part, okay, is 0 again by Green's theorem. Why? Because this is an exact formulation, and Q sub x is equal to P sub y, because the back point 0, 0 is not inside C2, which is applicable since 0, 0 is not inside C2. So this is the same as the second part. So this is exactly integral C2 of 2x minus 2 over x minus 2 squared plus y squared dx plus 2y over x minus 2 squared plus y squared dy, and say it is B, okay, by direct calculation. We don't expect it to be 0. Actually, it's minus 2 pi or something. Okay. On the other hand, as C, okay, if we consider a C3, which is something like this. It's counterclockwise, smooth, everything is nice, okay? But, okay, it contains both bad points. So, integral over C3 of P dx plus Q dy would be, okay, because of our previous observation, if you draw small circles around them, okay, it will be the sum of the integrals here, which were a plus b. Okay. So how many bad points you have inside, okay, what their values are, plays a role here because of the trick of putting out the bad points outside of C in some sense by calculating the integral over Ct, where we can apply Green's theorem. Okay.